we now start a series of videos that have to do with the development of quantum mechanics. As we will see, quantum mechanics is the current theory that explains the structure of atoms and molecules. And it turns out that to understand very well what quantum mechanics means and how it's developed, it's also very important to understand how electromagnetic radiation works. Electromagnetic radiation is just another way to talk about radiation that is very well known to us, for example, visible light. Okay? It turns out that the way to envision what electromagnetic radiation is to assume that we actually have a propagating electric field. Okay, so we have an electric field that is moving away from a source, and it's oscillating in time, going through peaks and valleys. Okay, and associated with this, you actually have a perpendicular magnetic field. Okay, so that will be the electric field part of this wave, and then you will have a magnetic field that will be perpendicular to this and reaching peaks and valleys in a different plane at the same time as this electric field is. Okay, there's various types of electromagnetic radiation, and of course the one that is more common to us would be the visible part of the spectrum. Okay, and if we actually take all of those sources of or types of electromagnetic radiation and we order them in terms of increasing energy going this way, okay, it turns out that visible would be right here, but then ultraviolet would be a little more energetic, even more energetic than that you would have X-rays. And there's other types of even more energetic radiation right here, but then less energetic than visible, you will have infrared, and then you would have microwave, and then you would have radio frequencies. Okay, so this is kind of a good cross-section of all of the types of electromagnetic radiation that you can have. All of them, again, have this characteristic of being an oscillating electric field propagating through space with a perpendicular magnetic field also going through space. All right, so let's talk about some of the properties of this electromagnetic radiation. First, it doesn't have any mass. Okay, so this is just a field. It's not a particle, no mass associated with this. Second, it actually behaves as a wave. Okay, and a way to prove this is to do something that is called a double slit experiment. Okay, so we know that waves can interact with other waves. Okay, and for example, if you have two waves that are interacting in this manner, in which you can see that the time at which the amplitudes and the values are appearing is in phase, is at the same time, then the result of this would be an amplification of the wave. Right? So what you have is that the resultant wave would be the sum of those two waves. This is what we call constructive interference. Conversely, you can actually have the destructive interference version of this, in which this wave that you have on top can interact with a wave that is exactly opposite to it, okay? And then you will have destructive interference. Okay, so then you will have that these two waves will cancel each other out, and then the wave will disappear. So actually a way to prove that visible light and infrared light and microwave radiation, all those behave like waves or are waves, is to actually prove this type of constructive and destructive interference through an experiment that is called the double slit experiment. Okay, so in a double slit experiment, what you do is you send light to a structure that looks like this. Okay, so you're going to be sending light or any type of electromagnetic radiation, and then that light hits a wall, but this wall has two slits. Okay, so depending on the size of the slits, what you will observe is something that is called diffraction, and that is that the wave can actually do this type of behavior in which it bends around this amplitude, these slits right here. And the idea is that now what you actually have here is a region where the waves that you have propagating through this slit and through that slit, those two waves now actually are converging in the same region of space. Okay, and then they can interact constructively and destructively, and sometimes they will interact constructively, sometimes they will interact destructively. And then what you actually see is, if you put here a photographic film or something that is able to score this radiation, you will see that there would be bright lines where you actually have constructive interference, and then dark lines where there's no wave because of destructive interference, right? So actually, you actually get this type of pattern right here that again is a consequence of having constructive or destructive interference in this double slit experiment, and that proves that electromagnetic radiation is a wave. If it wasn't a wave, then what you should see is that, well, this field continues and you only score here and there. You don't get this diffraction pattern throughout the photographic film. Okay, so again, that is an experiment. It was done about a couple hundred years ago, and that proves that visible light, for example, or infrared or UV, is a wave. Okay, so because it's a wave, we can then try to study some parameters of the wave. We've talked already about the energy of the various types of electromagnetic radiation, and we can talk about other aspects of it. One of them is the speed. Okay, the speed of the wave in a vacuum of this electromagnetic radiation is a constant number. Okay, 3 × 10⁸ meters per second, which is what we commonly ascribe to the speed of light. Well, it turns out that this speed is not only for light, it's also for X-rays and microwave and radio frequencies and so forth. Okay, and again, this is constant as long as you're in a vacuum. Now, there's other things that we can talk about in these waves, and one of them is if we map here intensity versus length. Okay, the wave looks like this. Something that we call the wavelength is simply the difference in length between two peaks of amplitude. That's what we call wavelength, which is denoted with Greek letter lambda. Okay, so the wavelength changes from type of electromagnetic radiation to a different type. Visible, for example, has wavelengths that are between 400 nanometers and 700 nanometers. Okay, then UV will have shorter wavelengths. Infrared will have a little bit of longer wavelengths. Okay, so the longer the wavelength, the lower your energy. Radio frequencies, for example, have wavelengths in the meter time scale or length scale, which is much longer than what you have for visible, which again is 400 to 700 nanometers or so. Okay, so this is what we describe the wave as in terms of wavelength. But then you also have frequency. Okay, notice that because this is propagating in time, you can actually put here a detector and see what is the time that it takes for two of these peaks to pass through. Okay, or the difference in time between one peak passing and then the next peak passing. That's what we call the frequency of the electromagnetic radiation, and this has units of per second. Okay, so typical UV-Vis type of frequencies will be 10 to the 15 per second. Okay, so it's propagating very fast. And that also depends on the type of electromagnetic radiation that you have. All right, that is that the wavelength has units of meter. Okay, so there's a relationship between these three parameters that we have right here, and it turns out that the speed of the electromagnetic radiation is equal to the wavelength multiplied by the frequency. Okay, those two things are the same, and notice that the units work out. Meter per second is equal to speed meter per second. Okay, so if you know the wavelength, then you can calculate the frequency. If you know the frequency of a wave, then you can calculate the wavelength. Okay, these are all interesting calculations. Now, there's one more thing that we can use to characterize this type of electromagnetic radiation. We actually sometimes talked about something called the wave number. Okay, and the definition of the wave number is simply equal to the frequency over the speed of the wave. Okay, that is that the units of this wave number would be meter to the -1 in the SA system, but typically we like to use this as centimeter to the -1. Wave numbers are very useful when we try to characterize infrared radiation, because infrared radiation has wave numbers which are in the that go from the few hundred to the few thousand wave numbers. Okay, so again, this type of wave number will be something useful in units of centimeter to the -1 when we talk about infrared radiation. Okay, so this concludes our survey of what electromagnetic radiation is, the types that you have, and some of the properties that we're going to be using to characterize them.